Hi, so in this video we're going to finish off ordering differential equations with a little topic called boundary value problems. So far you've looked at what are called initial value problems, where we start at an initial time, we integrate forward in time. So you don't often have one set of initial conditions that constrain the problem. But another class of problems involves things which involve two boundary conditions, often a second order differential equation, and also very common in modelling problems. So to complete our survey of ordinary differential equations, we must solve them. The other thing is that we will encounter our first sort of example of using matrices, which will then blend nicely into the third part of this module, which is the matrices bit, which we'll get into after half term. Okay. Okay, so we're moving on from initial value problems to, so before we looked at initial value problems. And that was involved time stepping them forward. So this is a very common sort of applied mathematics problem, especially when you get into year 3 and year 4 and do projects, or even the group projects you do this year with this module. You'll come across a set of ODEs that need to be integrated with time. So the methods are very important, and that's why we spend the most time on it in some way. But another important class of problem we must at least treat initially is but another set of problems is boundary value problems. BVPs, if you like. We're just going to consider one as an example, but it illustrates a lot of the problems. So consider now, instead of a first order ODE, we consider a second order ODE, but instead of in time, it's in X. What we're considering is a problem now like this, where we have two endpoints, say at x equals 0 and x equals 1. So this is our x-axis now. And we're constraining y to be a certain value, y of x of 0 equals 0, say, and then maybe also y of x equals 1 equals 0. So these are our boundary conditions, hence a boundary value problem, and they define the setup. And then we solve the ODEs, really solving the solution is what really fits in the middle, really, at any one time. So one way of thinking about a boundary value problem is it's sort of an instantaneous solution to a problem with two boundary value conditions, whereas the initial value problem is you're starting off at initial time with initial conditions and then winding forward in time. So they're both classes of problems come up in real applied problems. So here we're going to have we're going to solve on the domain x is between 0 and 1. That's going to be our boundary. And so the endpoints on this domain are our boundary conditions. So we're going to have y at x is 0 equals 0, y at 1 equals 0, 2. Okay, so that's exactly this problem, that we have our y solution has a value that boundary conditions. Okay. So for the time being, the best way to think of the separation between initial value and the boundary value problems is one is kind of an instantaneous solution in X, the other is a time integrated solution. So we now discretize like we did before in X in space, so such that X then goes to xi is I times delta X. By the way, I is not the square root of -1 this time. I is just an integer. Okay, I is an integer, positive integer. Okay, and delta X has a name. Is called grid length. And these are two bits of words. It's very important to get a handle on. And people who do well at this module do get it. It's called, but remember we had the time step, and as you say, don't keep using this notation of H. It's a really kind of a very introductory way of doing it. The more sort of general and appropriate notation is when you have a delta and whatever variable you're discretizing, because you have delta t and you have delta y, you have delta x as well. But delta x is called the grid length. Okay, and these sort of bits of nomenclature show you know what you're about with numerics. If if someone says what's a grid length in your method, you can come up with an answer. What's a time step? Okay, so get used to using these words for this problem. And what we do is we discretize d2y by dx squared using second order Taylor series problem. Taylor series expansion. From earlier in this section of the module. Okay, so basically you're just using the result. I'll give you the reference in the lecture notes if you want. Go back and it was when, right at the beginning of this section, we wrote down formula for the first and second order derivative. There's an expansion. So what I'm referring to is page 21 of lecture notes, equation 3.7. And all we're doing is we're changing h to delta x. Okay, instead of using delta x. So therefore we get d2y by dx squared equals, is approximately equal to this equation, which is y of I plus 1 minus 2y of I plus yi minus 1 y over delta x squared. And we know this is of order delta x squared error. Okay, so it's a second order approximate of d2y. So y I plus 1 corresponds to yx plus delta x, yx minus delta x, and then minus 2. But you remember these coefficients came up before, kind of called Laplacian coefficients. You've got 1, minus 2 and a 1. So it's a very common formula. It's one you should remember, really. So that's the main idea. And then obviously our function f just goes to a discrete value f of I. So the equation we're solving then is this. We have y I plus 1 minus 2y of I plus y I minus 1 all over del direct squared equals f of I equals 1 to all the way up to n minus 2. So we're considering there's n points in x. Okay, and that's just doing it over the interior points. That's what it's saying. So I goes from 0 to n minus 1, and these are basically what I call the interior points, i.e. the non-boundary points, and then obviously we'll fill in the boundary values later. But let's just look at this. So what we've got is something quite different from your ordinary differential equations. You can't rearrange this in the same way and have a start with the 0 value of I and then just step it forward like you did in x. It doesn't work like that. We can't solve this in the same way as the IVP in initial value problems. We need to solve for all yi's, for all values of all yi's, all the values of I for all the values of n at once, if you like, right, at one time. And the way to do that is going to be so we're going to use matrix inversion to do that. So we want to know the values of y at any time. We can't just step it forward, it doesn't work. You can try doing it like that, but what reason it doesn't work is because you've got two boundary conditions, right? So if you started at y is 0 and just try to step this forward, then you get to the other boundary and you've got the other boundary condition that you've got to satisfy. So it won't work. You then have to redo it, unless you do it empirically, and lots and lots of times it won't work. So to satisfy your boundary conditions. So it's conceptually it's quite a different approach, but it's very important we show you this because and that's the other. You can often go through a very complicated code and say, look, that's a sort of a time stepping bit there, and that's a matrix inversion bit, and that's why we solve it. Okay. So just before we go to write down this matrix problem, we arrange as so we multiply through by del direct squared, and we get y I plus 1 minus 2y I plus okay. And that's for I equals 1 to n minus 1. And we want to write this down as T y equals del direct squared f. Okay, so the underline are vectors, and the T is a matrix. And so y is a vector containing all your yi's. and F is a vector containing all your F values. Okay. Of course, delta X is a fixed. It's just your grid length is just a constant. So you can see, even just there's a reason it's called a T, and I'll make it clear as we go through, that if we could invert this matrix problem, invert T, then we get Y, which is a vector containing all the Y's, so we get our solution. So we can write it down in this form, and you'll see that in order to have this differencing formula and the boundary conditions all satisfied at the same time, its natural place is to put it into a matrix. Okay. So that's the last thing I'm going to do. I'm going to go through this carefully next few minutes, and then I propose I pick this up after half term as we go into the matrix section of the module. So I'm going to use a whole board for this. We've got a matrix. This is going to be our matrix T. This is going to be our vector in a column form of Y. And then I'm going to put a constant delta X squared in there. And then we've got our right hand side. So this is a sort of specific case of if you do certain courses that, especially in sort of theoretical physics or things like this, a discretized function often makes itself into a vector. So if the Y function makes itself into a vector when it's discretized, which makes sense, you've got all the different values, and it equal that F goes into a vector. And an operator, a differential operator, makes itself into a matrix. Okay, don't worry if worth thinking about. But this, let's just look at Y, the thing we're solving for. We've got Y0 and we've got Y big N minus 1 there. Those are our boundary values. So what I'm going to do is I'm going to start actually by doing the boundary values, because they're so important. They define the problem, and we know the boundary values are that we're setting it to 0. So what we're going to do is, this is a big matrix, it's M by N matrix, but let's just fill in the boundary value from. So if I multiply this element 1 by Y0, it's going to equal 0. So that's the X equals 0 boundary condition. And equally at the other end, if we put a 1 down there in the diagonal element, that gives that's the Y X equals 1 equals 0 boundary condition. That's good. That's the boundary conditions in place. And then I'm going to just give a general point in the middle, a certain value of I. Remember, I runs from 0 to n minus 1. It has n values. Okay, so that's your little central portion. Now with this one, we know that it equals, this is our discretization I just wrote down, that this central element has minus 2, so minus 2 times yi equals f of I. Yeah. And 1 times yi minus 1 is f of I, and then 1. So let me try and just use a different colour pen to highlight what's going on. You've got this sort of central, so this is just one of many different elements. This is the diagonal here. These two end things are on the diagonal. Then you offer 2 diagonals there. That multiplies this vector yi, so that minus 2 multiplies by yi, the 1 multiplies by yi minus 1, the 1 tries multiplies by y plus 1, and that equals f of I. So that central element is giving you all the information of that general formula. So all the other elements in the this matrix have the very are repetitive. Let me fill that. Repeat. So the row above you have a 1 minus 2 and a 1 minus 2 like that. And a common notation is just to put dots to show that it sort of repeats. So we've got a matrix here, a big matrix, but a lot of the elements are 0. So of course I haven't filled them in, but where there's space, that means there's basically zeros in here that I haven't shown because it just will make the, sorry, apostrophe is used wrong. So there's zeros in this white space here or here, and then but we've got the boundary conditions in here that I've emphasized. Okay, so this, I'm conscious this is a completely, and this is why I'm sort of going to pause on this and have a and there's a neater LaTeX diagram on page 737 of the lecture notes of this. Have a look at both of these, see if you can understand what's going on. So it's quite a different approach from the IVPs, and the way I can understand it is that we want to solve all the values of y at once. You know, quite a common problem with this is like a beam suspended between two endpoints. If you want to find a solution for that, often you have to solve it as an instant, and the way to do that then is to encode the yeah, this is a diagonal, by the way. I think it's encode the differential equation in a matrix, and also then put in the boundary conditions, and then you can then invert that matrix to find the solution, and then you can be satisfied rather than empirically trying to start at one end and get the boundary condition at the other, which you might be there forever doing that. You've got it written down once and for all, and you know when it's inverted, you've got the boundary condition satisfied and you've got the differential equation satisfied. So all this is a small section at the end. Conceptually, this is quite different, and it takes a while for people to get their head around. Now, I've got an example. There's an example code called that. No, I must put up on the LE page. It's called boundary value.m. That's a MATLAB code, and I will go through this after half term. But if you want to have a go at this and see it working in practice, that's what I say you pick up. Diagonal, yeah. So yes, so that's sort of something to look at and consider and try and understand over the break, and I'll see you again after half term. Okay, bye for now.